Hello and welcome to the Geomystic channel. Today we'll continue our three-part series on area with part 2, which covers areas of trapezoids, rhombuses, and kites. If you missed part 1 on areas of triangles and parallelograms, you can find that right up there. And if you'd like a printable guided notes worksheet that will follow right along with this video, click on the link down in the description. So to derive the formulas for the areas of trapezoids, rhombuses, and kites, we're going to utilize the area formulas that we already know from the previous lesson, which is parallelograms being base times height and the area of a triangle being half base times height. So let's look at a trapezoid. So by definition, a trapezoid is just a quadrilateral with one pair of parallel sides. So we have one pair of parallel sides here. The other two sides, doesn't really matter what they are. They might be congruent. If they're congruent, it's an isosceles trapezoid. But if they're not congruent, it's just a general trapezoid. Now, in a trapezoid, the two parallel sides are what we call the bases. Now, there's two bases. It doesn't really matter which one is which. We usually just call one base 1, or B1, and the other one we call base 2, or B2. The height of a trapezoid, we can't forget, just like with a parallelogram and in a triangle, the height of a trapezoid is always going to be perpendicular to the base. Now in this case we have two bases, so it's just going to be perpendicular to both bases. So the height of the trapezoid will always cross the bases at a 90-degree angle. Now to figure out the formula for the area of one of these things, what we're going to do is we're going to think about it in terms of a parallelogram. So what we could do is we could duplicate this trapezoid. We could take that thing, and if we picked it up, flipped it around, and placed it back over kind of right next to it, what we would have is a second trapezoid, just kind of upside down, kind of like this. Okay, where these two trapezoids here are exactly the same. I've just taken this one, kind of flipped it over to match this. What we have in total is a large parallelogram. And in this parallelogram, because we know that the two bases here, base 1 and base 2, are the same as these two sides, this would be base 1, okay, these are the same. This would be base 2 down here, so we can call that base 2 right here. This is really just base 1. And the height stays consistent throughout. So if I said I have a parallelogram and I want to find the area of this whole thing, we know that the area of a parallelogram is just base times height. Okay, so if I find the area of this whole parallelogram, I would take the whole base, which would just be the sum of these two lengths, so base 1 plus base 2, times the height, which is still just h. So if I think of this in terms of the parallelogram area, the area is equal to the base, which would be base 1 plus base 2. I'm going to put those in parentheses. Base 1 plus base 2 times the height, which is just h. Okay, so that would be the area of this whole thing. Now, this trapezoid, my original trapezoid, if that's what I want to find the area of, what portion of this whole parallelogram is just this trapezoid? Well, since I just doubled this trapezoid to make the whole parallelogram, this right here would just be half of the entire parallelogram. So if this would be the area of the whole thing, I know that half of that would get me the area of that trapezoid right there. Okay, so this formula right here, this is the general formula for the area of any trapezoid. You add the two bases together, base 1 and base 2, those two parallel sides. You multiply by the height, which again is perpendicular to both bases, and we will take half of that value. Okay, we're going to hold off with the examples until the end. We're going to go ahead and cover rhombuses and kites first. Now, with rhombuses and kites, although these are two very different shapes, they share a lot of the same properties. So in a rhombus, which by definition the rhombus just has 4 congruent sides, and in the kite, where we have two pairs of non-adjacent congruent sides, so these two are congruent, these two are congruent. To find the area formula for these two, we're going to utilize the fact that both of these shapes have perpendicular diagonals. Okay, so the diagonals, which are just the lines that go from one non-adjacent vertex to another. So there's the diagonals for the rhombus. Those are the two diagonals for the kite. Okay, so a property for each of these two shapes is that the diagonals are perpendicular, meaning they cross, once again, cross at 90-degree angles. Okay, so because of this fact, what we have done with both of these shapes is essentially just cut them into 4 right triangles. So each of these shapes, when I draw those diagonals, I've got 4 right triangles in each one. And because we know how to find the area of a triangle, that's going to make this, this formula kind of make sense here. So let's start with the rhombus. Now, a side note with the rhombus, don't forget that a rhombus is also a parallelogram. So if I did have the base and the height of the rhombus, I could just take base times height because it is a parallelogram. But if you have the diagonals, or you know some information that can get you the diagonals, or you don't have a base or a height, this is another way to do it. Okay, so for a rhombus, we've got the 2 diagonals. We'll call this diagonal, so this whole thing right here, we're going to call this diagonal 1. And this whole diagonal here, this whole diagonal, my brain's running out, let's try a different color. This diagonal we're going to call diagonal 2. There we go. Okay, we'll call that diagonal 2. So diagonal 1 is here, diagonal 2 is right here. Okay, so what we're going to do is we're going to look at this in terms of the triangles. So if I were to find the area of, say, just this triangle right here, okay, we know that the formula for the area of a triangle is just 1/2 base times height. Okay, so that's for any triangle. So if I'm looking at this triangle right here, to find the area of this triangle, I would take 1/2 base times height. Now we're in luck here because we have a right triangle, knowing that the base and the height would cross at a 90-degree angle. We're just looking at these 2 pieces here. So if I look at this piece, call this the base, and we'll call this the height, because a rhombus is a parallelogram, the diagonals do bisect each other. So I know that this piece right here is just half of the entire diagonal. Okay, so this being 1/2 of diagonal 2, I can call that the base. So using my formula, I've got 1/2 base times height. So 1/2 of the base. The base we're going to call half of diagonal 2, meaning that's this right here. Half of diagonal 2 is the base of that triangle. The height of that triangle is this piece, which is half of diagonal 1. So the height is half of diagonal 1. If I simplify this a little bit, I've got a half times a half times a half. So 2 times 2 times 2, this is really 1/8. So I've got 1/8. And then diagonal 2, diagonal 1. I'm just going to rearrange the order here and just write diagonal 1, diagonal 2. It doesn't really matter. Okay, so the area of this one triangle right here, the area of that would be 1/8 diagonal 1 times diagonal 2. How many of these triangles make up this rhombus? Well, if the rhombus has 4 congruent sides and the diagonals bisect each other, these are all 4 congruent triangles. They're all the same. So if one triangle has an area of 1/8 d1, d2, that means all 4 of these triangles have that same area. So all I need to do is take this area and I'm going to multiply it by 4 to get the area of this whole rhombus. And if I take 1/8 times 4, that would be 4/8. And 4/8 reduces down to 1/2. There you go. Okay, so the area formula for any rhombus is 1/2 d1, d2, where d again stands for the diagonal. Diagonal 1 times diagonal 2. Now, the same idea also works for a kite. We're going to kind of do the same thing. It's a little bit different, but still utilizing that triangle property. Okay, so if we take a look at our kite here. So there's the kite. We take our diagonals, which are here. And you can see we've got those 4 triangles because the diagonals are perpendicular. They're 4 right triangles. Okay, but this time we don't have 4 congruent triangles. Obviously, these 2 triangles here are not the same as these 2 triangles here. So what we're going to do is we're going to kind of look at these triangles. So this one right here, and then this one down here, which is going to be the same as this. So this line of symmetry down the middle cuts this kite into 2 congruent triangles. So looking at these 2 together and then these 2 together. Now, go ahead and call this right here. This is going to be diagonal 1. Well, we'll switch it. We'll call this diagonal 2. This one's diagonal 2, and then this one right here, this is going to be diagonal 1. We don't have to change the order later. Okay, so looking at this triangle up top, this whole thing, the area of this triangle, again, area of a triangle is half base times height. The base of this triangle is just D1. That entire diagonal is the entire base. So half of the base is D1, times the height, which is going to be here. Now, because this is the entire diagonal 2, that line of symmetry is cut it in half. So this piece, the height of this triangle up top, is going to be half of diagonal 2. So I've got half diagonal 2. Again, cleaning this up, I'm going to go ahead and multiply half times a half, which is 1 over 4. So I've got 1 over 4 times diagonal 1 times diagonal 2. Okay, so again, that's the area of this one right up top. But because these two triangles, this one and this one, because those two triangles are the same, they have the same area. If the area of this one is 1/4 diagonal 1 times diagonal 2, so is that one. So I can just multiply, again, this whole thing times 2. There's 2 of those triangles. And 1/4 times 2, 2/4, which is just 1/2. And we see the same formula, 1/2 diagonal 1 times diagonal 2. Okay, so for any kite, any rhombus, using those diagonals, all I have to do is take 1/2 of the length of each diagonal, multiply them together. All right, let's do some examples. We'll stick with the kite since that's fresh in our minds here. Okay, so there's our kite. Again, we've got perpendicular diagonals right there. And let's put some values in. Let's say this is 3 inches. We'll call both of these 4 inches. Not drawn to scale, by the way. And then this down here, we'll call that 6 inches. Okay, so we've got the 2 diagonals in pieces here, but we can take the entire length in just a minute. So we use our formula for any kite. The area is 1/2 diagonal 1 times diagonal 2. We just need the lengths of each diagonal. Doesn't matter which one's 1, which one's 2. So let's say, we'll say this is diagonal 1. So the entire length, meaning the 3-inch segment, the 6-inch segment, the entire length is going to be 9 inches. Add those together. Diagonal 2, the entire length of this segment, the two 4-inch segments, add those together, you get 8. 9 times 8 is 72. And half of 72, or half times 72, is 36. Don't forget this is an area, so we're looking at square units. In this case, we're in inches. So the area of that kite would be 36 square inches, or inches squared. All right, so when you have all the pieces, when you have both diagonals, it makes it real simple. You really just plug it into the formula and you get your answer pretty quickly. Now, sometimes you don't have all the necessary information. Sometimes you're either given extra information or you're missing some pieces. Let's look at one where we do have to go through a little bit of a process to find one of the missing parts. So let's say this is a rhombus, all 4 sides the same. So we've got our rhombus, there's our diagonals. Perpendicular, and let's say that we'll call this 8 centimeters here, and we'll call this 10 centimeters up top. And that's it, that's all I'm going to give you. Okay, so 10 centimeters up here, we've got 8 centimeters here. So we really have to think about rhombuses in general, what we have, and what we need to be able to solve this area. So once again, my area formula is 1/2 diagonal 1 times diagonal 2. So my first question would be, do I have either diagonal? Do I have the length, the entire length of either of these 2 diagonals? And the answer would be yes, I do have one of the 2. I know that this entire diagonal right here, if this piece is 8, the diagonals do bisect each other in any parallelogram, so this would also be 8 centimeters. So for diagonal 1, we'll call it my entire diagonal length, 8 plus 8, that would be 16. Now diagonal 2 is here, and I don't have either of those two pieces. So I've kind of run into a little bit of a stumbling block. I'm missing diagonal 2, but I do have one more piece of information that is going to help me figure out what diagonal 2 is, and that's this piece up here. Okay, so remember earlier when we derived this formula, we said that we've got 4 congruent right triangles with this thing. So what I want to do is I just want to look at this right triangle up top. Okay, if you've been in geometry for any length of time, you've probably dealt a lot with triangles, and you've probably dealt a lot with finding missing pieces in triangles, especially right triangles, which is what we have here. So think about a way that we could use 2 sides of a right triangle to find the third side. Because if I know this third side, then I can figure out what the entire diagonal would be. So my question is, what can I use to figure out A if I know B and C? Maybe that rings a bell. In any right triangle, we know that a squared plus b squared equals c squared. That's the Pythagorean theorem. That's what we're going to use for this right here. So Pythagorean theorem says that if I know 2 sides of a right triangle, I can find the third, because the relationship that a squared plus b squared, call 8 squared, is equal to the hypotenuse squared, 10 squared. Okay, if you don't remember this, I have a video on the Pythagorean theorem. You can find that right up there in this corner. So I've got it set up. All I have to do now is square a few of these. 8 squared is 64, 10 squared is 100. I'm going to subtract the 64 from both sides. And I've got a squared equals 36. Last step, to get rid of the square, I'm going to square root both sides, and the square root of 36 is 6. All right, so we got what we need. So I know that this value, the length of that segment right here, is 6 centimeters. Okay, using the Pythagorean theorem, I got that piece. If I know this piece, I really know this piece because, again, diagonals bisect each other. This is also going to be 6, which makes my entire diagonal 6 plus 6, that's 12. Okay, so we kind of have like a little intermediary problem in between finding my 2 diagonals. All right, last step. I'll go ahead and multiply these things out here. We've got 16 times 12. 16 times 12 is, I believe that's 192. So I've got half of 192. And half of 192 is 96. And we are in centimeters. So 96 square centimeters for the area of that rhombus. Okay, sometimes it can get a little confusing when you're missing some pieces, but again, start with your formula, figure out what you have, and then kind of work backward to figure out what else do I need, what do I need to know, and then look at your picture to figure out what it is you can do to get those missing pieces. Okay, utilize those triangles. That's usually going to be your best bet. All right. Let's look at a trapezoid. All right, so let's say we've got a trapezoid where you got 8 meters, 12 meters. We'll say this is 5 meters, and we'll say this is 3 meters. Put the right angle down there. Okay, so here's our problem. Find the area of the trapezoid. Okay, so if we remember back to our formula for the area of a trapezoid, we got the area is equal to 1/2 base 1 plus base 2 times the height. That's what we got. So at this point, we just kind of look at our picture, look at our formula, decide if we have what we need. I would say, yeah, we have what we need. We actually have more than what we need. If I look at the 2 bases, once again, it doesn't matter which one's base 1, which one's base 2. So I'm going to say base 1 is 8 and base 2 is 12. So 8 plus 12 times the height. Okay, so you got to be careful just a little bit. What's the height of this trapezoid? Is it 5? Is it 3? It's 3. It's 3 because that is perpendicular to both bases. If it's perpendicular to one set of parallel lines, it's perpendicular to the other. All right, so the height is 3. The 5 is just extra, don't even need it. Okay, so work through this one. 8 plus 12 is 20 times 3 on the outside. We'll go ahead and multiply first by the 3, so 20 times 3 is 60. And finally, half of 60 is 30, and we are in meters this time. So the area of that trapezoid is 30 square meters. Okay, so this is one, once again, where we have everything we need. We just have to use the formula, plug everything in, disregard any information that we don't need, utilize the information that we do. Okay, let's do one more. Always easiest when we have what we need. Can get kind of tricky when we don't. So let's take a look at one of those. So we got 4 up top, we'll say 6 across the bottom, and we'll put a 45-degree angle in the corner. Okay, so once again I'm going to start with the formula. 1/2 base 1 plus base 2 times the height. Okay, so think about what we have. We've got really 3 values. We got the 4, the 6, we've got the 45-degree angle, the 2 bases. We've got 4 and 6 as our 2 bases. So this first part here, we'll fill in pretty quick. So base 1, base 2, and then times the height. So the height of this trapezoid is going to be right here. We know it's perpendicular to each base, but I don't have it. I got no value here. Where else could the height be? Well, the height can be anywhere as long as it is perpendicular to both bases. So what I'm going to do is I'm going to drop a line right there, perpendicular to each base. And you can see what I've done is I've cut off a triangle. Okay, I've cut off a triangle. More importantly, I've cut off a right triangle, and even more importantly, I've cut off a 45, 45, 90 right triangle. Since I had that 45-degree angle down in the corner, 45, 45, 90, knowing that gives us a lot of information about this thing. So if I look at this triangle, do I know any of the lengths of any of the sides? Okay, not specifically, but I can find one pretty quickly, because I know that this piece right here, okay, that piece is the difference of the 2 bases. If this is 4, I can kind of move that down here. This is 4. And if this whole piece down here is 6, I can take 6 minus 4. What's left over? It's 2. Okay, and here's where knowing your special right triangle rules, this is where it's helpful. In a 45, 45, 90, it's also an isosceles right triangle. Your legs are congruent. Okay, legs are the same. Obviously, again, mine's not drawn to scale, but if it is a 45, 45, 90, your 2 legs are going to be the same length. Okay, so if this leg is 2, I know that leg is 2, which means my height is 2. Okay, so don't forget about those special right triangles. Those always come in handy. I've got what I need. 4 plus 6, that's 10. So I got half of 10 times 2. Half of 2 is just 1. 1 times 10 is just 10. In this case, I didn't give you a length or a dimension, didn't give you a label, so we can just make it up. We'll call it units squared. All right, so that wraps up part 2 of our area study. Next week in our 3rd and final lesson, we'll dig into finding areas of any regular polygon. It's going to be a good one, so don't miss that one. You can help out the channel by giving this a thumbs up and subscribing to the Geomestic channel to see more videos just like this. Thanks for watching. We'll see you next time.